Now, we're most pleased to be delivering to you today some timely expertise about how to meet new regulations and standards with a focus on the medical device industry. Is hosting today's presentation about Are Your Medical Devices Ready for IEC 60601 3rd edition, with our guest speaker, Mr. John Hansen. Now, John holds a BSEE from Utah State University and has over 31 years of experience in reliability engineering, including 20 years in risk management alone. He has a wealth of expert knowledge in the medical device industry, and we are most pleased to have him as a member of our expert panel today. Additionally, Senior Applications Engineer, Mr. Neil Dortenbaugh, will also be presenting. And Neil holds a BSEE from Colorado State University and brings over 14 years of HALT&HASS expertise to the panel. At this time, I would like to introduce Mr. John Hansen to get this presentation started.
Today we're going to talk about several things that are related to both risk management and reliability engineering. Over the years, as I have worked in various industries and worked specifically in the medical device industry, it's become very obvious that there are many similarities between risk management and reliability engineering. In fact, many companies combine those two disciplines. We'll talk today about some of the reasons for that similarity between those two things and how we can use that to our advantage as we meet the requirements that are imposed on us by the regulatory community. And we'll talk specifically about a couple of examples of how reliability engineering principles and tasks can help us meet our requirements, our risk management requirements. So first, let's talk a little bit about reliability engineering and how it can play a role in meeting our requirements. Reliability engineering is aimed specifically at eliminating failures from our field of products, whether they are design-related failures, whether they are failures introduced during the manufacturing process, whether they are inherent failures. We want to minimize both the failures and the impact that those failures have on our fielded product. So that's what we try to do with reliability engineering in a nutshell. I know that that is an oversimplification, but let's move on from there to talk about some definitions. So reliability engineering is an engineering discipline, and as we talked about, its purpose is to make our products robust, to make sure that they don't fail when we don't want them to fail, when we can't have them fail. So reliability can be defined as the ability of a system to meet its required function over a stated period of time, and to meet that requirement, to meet or exceed that requirement. Risk management is very similar, as I said. Risk management involves the identification and assessment of risks associated with the use of the equipment. Now, these risks can come from several different areas. They can come from equipment failure. They can come from human error. They can come from misuse of our product. They can come from several different areas. They can be environmental risks as well. So, much like reliability, risk management is aimed at identifying, assessing, and taking action to eliminate risks, to eliminate the problems wherever they come from. Today, we will focus mostly on risks related to equipment failure. As we get started, I want to talk a little bit about the 60601 3rd edition standard and what its purpose is and what it does. Basically, 60601 3rd edition combines many of the old 60601 requirements into one standard. And based on the general requirements of this standard, it's requirements for basic safety and essential performance. And it has become a requirement for commercialization of medical devices. Most companies and most regulatory agencies, I will add, view compliance with 60601 as a minimum requirement to field our products. So the stated purpose of the risk management in both ISO 14971 and in 60601 third edition are these: to identify risks, to evaluate them so we know what risks we need to take action to mitigate, to then mitigate the risks or eliminate the risks, to verify that we have mitigated the risks, and then once our product is in the hands of the end user, to continue to monitor the performance to ensure that what we think we designed into the product as far as safety and efficacy is really what is being achieved by the end user. And as in anything, we may need to take corrective action if we find that we have a discrepancy between where we are and where we need to be. So let's talk for a minute about how reliability engineering applies to medical device risk management. In one way of looking at it, it's very simple. If we want to eliminate the risk related to failure of any device, and we can eliminate that failure mode, we have accomplished what we set out to do. So reliability engineering applications, as we seek to have a robust system, as we seek to eliminate failures that occur in our design from whatever source, then we truly have a huge impact on meeting the risk management requirements. We do this by having a robust product. How do we get a robust product? That's a hard question to answer sometimes, but it really is simply good engineering practices. In order to have a robust design, we need to have the proper specification. In order to have a proper specification, there are several things that we need to understand. We need to understand how our device is going to be used. We need to understand how long it will be used. We need to understand what, if any, are the allowable failures that the device can have. And we need to make sure, I call it derating requirements, but we need to make sure, in fact, that we have adequate design margin in order to ensure that we don't put stresses on the components in our medical device that will eventually create a failure. So from a risk management standpoint and a reliability standpoint, we need to basically take the same actions in order to have a robust design. We need to understand the potential failure modes and their effects. That allows us to prioritize the actions that we can take. We will never get to the point where we have a perfect design. We need to be able to have a logical understanding that allows us to design out those failure modes that will have an unacceptable effect on the product. In order to do this, we need to analyze the design. We need to understand where the failure modes can occur, what happens when they do occur, and what, if anything, we can do to eliminate them. We need to understand the inherent reliability of our product. That can involve several different things. That could involve a reliability prediction. That could involve understanding where the failures will come from. That could really understand through test, and we'll talk about this a little later, through test understanding what our design margins are and what our failures are going to be. As in any design process, we will need to make changes as we go through the process to improve our design, to improve and get to the point where we need to be. And as always, we need to verify that the changes we have made and the design that we have created is effective, and that we truly have the design where we need to be. The graph here at the bottom of the page shows what I'm talking about. We need to, when we have a situation when the lower operating limit of a component and the upper operating limit intersect, we have an area where failures can occur due to stress. So ideally, we will have our operational specs separated from those areas where failures can occur. HALT, which we'll talk about in much more detail as we go through this presentation, and I believe Neil will talk about that specifically, can help us understand and analyze and understand our design strengths and our weaknesses. When we understand what our stress limits are, when we understand what our design capability is, we are in a position to make good choices regarding our design. We can ensure a robust design. We can ensure that we identify potential risks related to failures. We can also evaluate risk mitigation and enable risk mitigation verification. As I said, Neil will talk much more about HALT as we go along. Reliability engine principles can also be very critical in post-market activities. When we have adequate information about the performance of our devices once they are in the field, we are in a position that allows us to determine whether or not the device is performing as we intended. We understand what failures are occurring. We can understand what the failure cause is, and how those failures affect patient safety. We can also understand and eliminate or mitigate further changes if we need to make them. We can make decisions regarding whether a product is experiencing unacceptable risk, whether it needs to be removed. So the point that I want to make here is the reliability and application here is very critical in both pre-market and post-market activities of our device. So let's talk a little bit about IEC 60601 3rd edition and some of the requirements. Now, I will say that I have only had time that this presentation only allows us to talk about a few examples of reliability and how that applies to 60601. As we go through all the standard and all the clauses, we find many places where reliability engineering principles can be used. But let's talk about some examples. In clause 4.3, for example, this is the essential performance clause, and it requires us to understand what our policy is for risk acceptability. Clause 4.3-1 talks about some particular tests that need to be done, and that how we will, as we go through those tests, ensure that we still have maintained the essential functions. So bottom line here is we need to understand what our equipment does and what's important to that equipment. And we need to understand that at the end of the day, after we have done all the required tests, all the required designs, that those essential functions have not been compromised. Now, that's easy to say, but how do you do that? How do you do that in real life? I would suggest that once we understand our design margins, once we understand what can fail in our design, we are in a position to ensure that we continue to meet all those essential performance requirements. Clause 4.4 talks about expected service life, and that we need to state that in our risk management file. That seems almost like a no-brainer, but too many times as we go through our product, we don't fully understand what our service life is going to be, and we don't fully understand the use environment of that device. I will give you an example. Let's consider a medical device that can be used in several different environments. A good example would be an automatic external defibrillator. Typically, you see these in the airport or in the wall of a doctor's office or a hospital. They are very critical. They hang on the wall except for the few seconds of use when they are critical to shock a heart back into an acceptable rhythm. Some of these devices, however, are carried around in the back of a police car or other areas where they have a different environment than they would if they were sitting in a doctor's office. They have vibration as the car rolls down the road. They have temperature cycling. They have a much different life scenario than would a device that hangs in an office. Now, to complicate that even more, there are many parts of the world where these devices could be found. Some countries would have a good infrastructure, good hospital environment for the hospital, good cleanliness environment, everything else. But we can't, as we consider the worldwide situation, we can't design everything we can't expect everything to be as it would in, say, a hospital in Europe or in the United States. So we need to consider very carefully what this device will see in its lifetime and understand how those different environments will affect the useful life of the product, will affect the failure of the product. Once again, this is something that can very well be evaluated using reliability engineering tools. The things that we've talked about, failure mode effect analysis, HALT testing, etc. All the things that we use in order to make sure our design is robust. Other examples. Clause 4.8 talks about components and wiring, and specifically looking at those components where a failure would result in a hazardous situation. This might be from exceeding their applicable ratings. It might be from several different areas. Specifically, that clause talks about the reliability of components used as a means of protection, and that we need to understand the reliability of those components. Let me give you an example of what I mean. If we have a device whose safe operation depends on the function of a part or a subsystem, we are required to know the reliability of those parts. We are required to ensure that they have been tested and assessed to meet the conditions that they will be used in. 60601 specifically talks about some types of components, motors, transformers, etc., where insulation could be compromised. Other examples of 60601 and how it plays into the reliability engineering discipline. Clause 4.9 talks about components with high integrity characteristics provided because a fault in a particular component can generate an unacceptable risk. These are the types of components where a failure really can't be allowed. A failure of any of these high integrity components would result in an unacceptable risk to the patient. In other words, if it fails, somebody's going to get hurt. The standard requires us to treat these components very specially, and they need to be selected and evaluated to be consistent with their conditions of use. And one of the interesting things here, conditions of foreseeable misuse during the entire expected service life of the equipment. When you think about this, this is kind of a daunting task. And once again, I would suggest that all of the reliability tools that we have in our reliability engineering tool belt are useful here. So when I talk about the reliability engineering tools available to us, what are they? Designed for reliability, there's not enough time to talk about all that means, but it's basically all those areas that allow us to design something for a high reliability. Reliability prediction can be used, especially prediction methodologies that, in my opinion, are focused on the physics of failure, to understand why something fails. to understand the mechanisms that create that failure so we can understand how those stress mechanisms will affect the failure rate of the component. A fault tree or a FMEA is very important in understanding our design and understanding what we need to do, in understanding what failure modes can be the most critical to us. HALT, as we talked about, and as Neil will talk about, can be very, very effective. Now, why is that more effective than a paper analysis? We have a device, and we systematically go about understanding how that device can fail, understanding both the failure mechanisms and the failure mode, and to some extent the effect that those failures will have, not only through analysis and our best information, but through actual test. HASS testing. HASS is very important. HASS stands for highly accelerated stress testing. We won't talk about that much today, but that takes many of the things we do with HALT testing and adds other stressing parameters. Specifically, would typically add humidity component. Now, as we look at the requirements and the checklist from IEC 60601, many of those test requirements require us to precondition the equipment to a use environment, typically with temperature, with humidity, and test that in the worst case environment. Once again, this is something that can be very effectively accomplished through our reliability test methodology. HASS, or highly accelerated stress screen, is something that we'll talk a little bit about as Neil goes into his presentation, but that is effectively the ability to screen out those components that are weak from whatever source that weakness might be. Basically, the unknown failure risk. The failures might come from the manufacturing process. They may come from a component that has a built-in defect. They may come from several different sources, but the whole aim at our HASS test, at our HASS screen, is to eliminate those unknown failures and make sure that they are not present when we send the device out into the field to be used by the end user. Life monitoring and analysis is critical. Many times this is called libel analysis. Libel is a specific kind of distribution that is typically used in reliability engineering, but it's not the only statistical analysis tool available. But I would suggest that life monitoring and analysis is very important. And CAPA, corrective and preventive action, are critical in ensuring that we not only meet the requirements of 60601 3rd edition, but that we continue to meet those requirements throughout the service life of the equipment. At this point, I'm going to turn the time over to Neil and let him talk about HALT and HASS testing specifically.
Thank you very much, John. It was good stuff, and it all ties in quite nicely to what we're going to talk about now in HALT and HASS. When you consider the basic functions of HALT and HASS in terms of risk mitigation, we're talking about finding more failure modes so that we can identify more risks and eliminate them. So we move unknown risks into the known risk category, and we have a tool for dealing with the residual risk associated with unknowns, things that we didn't expect to happen. Now, fortunately, we've got a fair amount of experience using HALT and HASS in the aerospace industry, and like the medical industry, reliability is critically important in those areas. You just can't tolerate a failure in certain applications. Medical is one of them, aerospace is another. And when failures happen in implantable devices, for example, of course, We've all heard the stories from different companies miserably going out of business from things like that. HALT and HASS are used in industries like this, where that high reliability is very important. Now, we are, as reliability engineers, facing challenges these days that are tougher than we ever have. We've got to keep the risk lower. We have new requirements for understanding and reducing risk at the same time that the business side of the money side of the business is seeing price competition. And we're having to deal with budget cuts, and we're having to deal with reduced test time, reduced resources, and time to market is being routinely reduced. We want it fast, but we still want to be sure that there's no risk. And there can't be a question of trade-off. We have to be sure that the risk is minimized, but we may even be dealing with technology we've never dealt with before. So we don't completely understand how it can fail or what can go on with it. If we're not dealing with new technology, then we're not advancing as a company. New technologies are what make us successful, but the failure characteristics of these new technologies can be poorly understood. There's not a lot of hard historical data. So when we're faced with these challenges and the overarching umbrella of we must reduce risk, we can feel like we're kind of between a rock and a hard place. But this is HALT and HASS are very valuable for meeting these challenges. Another challenge, of course, is that high reliability is becoming more important, and high reliability is meaning more and more. The mean time between failure is expected to be greater now than it was 10 years ago. And when you get in a situation like that, doing standard accelerated life testing can take a long time. And a failure found near the end of that accelerated life testing can be devastating to a timeline. I know that many companies have had to have significant delays to product release because near the end of accelerated life testing, they spot a design flaw. And this is not the time to find problems. This is the time to prove you don't have any. Finding them in that process is very expensive. And you have situations where high reliability, as in medical, means either extreme cost or tragic consequences. So you have to have that in-depth understanding of system operation and how it responds when a failure happens. Just as John has been discussing, understanding the product is really key to the risk management, risk identification and risk management. A few other challenges for high reliability systems. In aerospace and in medical, we're often dealing with high dollar systems that are manufactured in relatively low volumes. And there's a package of additional challenges associated with that. When you're running low volume, you have an inherently higher risk of variability. You're purchasing in lower quantities, so you have a risk of lot-to-lot variances that's higher than is the case in other industries. And if you've got lower quantities, you're more likely to have hand operations. There's inherent variability in those. So in a product where reliability is critical, you're saddled with these factors that make it more of a challenge. And when you're doing very high dollar systems, they're very reluctant to give you 40 or 50 to do accelerated life testing on. It costs too much. So we've got fewer samples to work with and a greater challenge to meet. And of course, as I discussed earlier, the final challenge is that a lot of times we're dealing with technology we've never dealt with before. We're continuously using higher speed devices. Every time you turn around, things are moving faster, signals are moving faster, measurements are happening faster. They're complex, interdependent subsystems, and it compounds all the difficulty. The solution, or part of the solution, to modifying a reliability program to deal with these challenges is to shift towards more of a failure-oriented testing, a discovery process early on in the design, as soon as it is feasible, to learn as much as you can about the product, understand how it fails, with an emphasis on forcing failures and understanding how it fails. And once you get into manufacturing, you realize you have a system that is less tolerant of variability in the manufacturing process or in your component supplier, and you need methodologies for dealing with that and maintaining higher reliability in manufacturing. All of these factors can be addressed and dealt with through HALT and HASS. And I'm going to get into a description of the basics of what we're talking about when we talk about the discovery process of HALT and the production screening process of HASS, and how they can help you address these issues. Now, we can talk about the HALT process in terms of 4 steps. First, we are stressing a product. We use thermal, vibration stresses, combined stresses, also stresses that are unique to your product. If there are other factors that can be incorporated, the more stresses you use, the more likely you are to find a fault, the more likely you are to take a risk from the unknown category and move it into the known and mitigated category. And you increase stresses until you find failures. You determine, have I found an operating limit, a soft failure? I take the stress away, the failure mode goes away. Have I found a destruct limit, or I'm actually causing a hard failure in a product? And then carefully understand. This is where the discovery process pays off. You've got, when you have a failure in your hand, you've got gold in your hands. And you need to do failure analysis in order to understand it and get down to the root cause of it and gain new levels of understanding of your product that you can't get any other way unless you force the failures to happen. See if there are improvements that can be made, corrective actions to be taken. This is something I can fix, or is this something that is what we call a limit of the technology? We just can't do anything about it, but we understand it, we understand its effects, and we can intelligently conclude that the fault mechanism is tolerable. The key is intelligently conclude by doing failure analysis and understanding the product. If we have achieved our maximum robustness, that is, we've hit the wall for limits of the technology, made all of the improvements that we can reasonably make to eliminate risks. If we haven't done that yet, well, it's time to continue the loop and step stresses up higher, maybe switch to the next stress, continue the series until we've done everything we can to achieve this maximum robustness, which means that we have identified as many potential risks related to product failure that we can and have identified the solutions for those. Once that is complete, and this is really the HALT process here, once that is complete, now we can take these results and use them to move into HASS or HASSA, the Highly Accelerated Stress Audit. And these tests use limits based on what we found here. So it's important that we go through this process before we move on here. By identifying what the product can actually tolerate and testing to those levels, rather than trying to test to levels of intended use environments, we're able to spot new risks before they turn into something that can show up in quantity in the field. We catch them at the very earliest stages and eliminate the risk before the product gets out the door. Another way to understand what we're talking about in HALT&HASS is the concept of the margin improvement process. John talked about the importance of margins and the basic concept of derating to create products that are more rugged and therefore lower risk. Here you see operating limits and destruct limits that have been identified in a HALT and the actual operational specifications for a product for a particular stress. Must be the thermal because we have upper and lower limits defined. HALT is usually done on a small sample, 4 to 6 units. So we have a few points. And if you just look at the points and say, okay, my operating limits are fairly well outside of my operating specs, what we have identified is our margins, the destruct margin and operating margin for the product on those samples. The trick is that there's a distribution around those margins. We've got just a few units, and it's not just one failure mode. These distributions are really composed of many failure modes. And if we eliminate a particular failure mode that may allow us to move this operating limit out a little bit here and find a new failure mode. Many, many things cause this distribution to be the way it is. But when this tail gets down into your operating specs, that means that we're going to be having out-of-box failures or very early in life failures, even though on the few units we tested in HALT, we have limits that are operating limits that are outside of our operational specs. By further derating the product, by pushing those margins out, eliminating the failure modes that we find in here, then what we wind up doing is getting these unknown distributions pushed out further away from our operating specs. By doing this, we make the whole system more tolerant of variances, so things don't show up as problems in the field, even when something shifts here. And as things age and fatigue in the field, we expect to see these creep in and as components drift out of spec, and we wind up with a product that has a longer life in the field before we begin to see defects in the operational range. When we have tested outside of operational specs and maximized these margins as much as makes sense. And as I said, the failures that you find when you're doing HALT and you find failures and you eliminate them, push them out, those failures are typically very similar to the failures that you see in the first 6 months of a product's life in the field. We're not finding really complex things. We're finding relatively straightforward failures to fix. We're just finding them early, and that's the value. And if we look at IEC 62506, talking about where to use HALT and HASS in the product life cycle, we talk about HALT being a maturity building process and HASS being a maturity confirmation. The HASS, the production screen, really is intended to give you an early warning that some new failure mode has crept in that has caused those distributions to shift. And when we develop a HASS screen, the basic idea is we understand what our operating limits are, that's these lines, and we develop a thermal profile that stays within the operating limits. We typically guard band that by 80%. So we don't expect to see products failing here. We expect to see them operating normally. We also vibrate at about half the destruct limit that we identified in HALT testing. The relationship between fatigue and stress level is logarithmic, so the stress level or the fatigue that the product sees at this stress level is much, much lower when we go to the half limit. Then we will do a proof of screen to demonstrate that we're not taking an unacceptable amount of life out of the product. This whole process of using HALT&HASS to improve reliability in areas where reliability is critical is becoming much more widely adopted. Test requirements for launch, upper stage, and space vehicles, I believe that HALT&HASS is being worked into those now. GM's been using them for years, Airbus, etc. We see the whole process becoming more and more adopted simply because it saves an awful lot of time and money. Boeing used HALT&HASS in '94 on all of the key avionics components of the 777. Airbus actually published a HALT guideline saying, if you want to be an Airbus vendor, HALT has to be part of your design process. And do that before your design verification. In 2011, Hamilton Sundstrand said HALT&HASS are key to meeting reliability challenges in aerospace. So you can see the value that's brought there. So in general, we're using HALT&HASS to reduce both the known and the residual risk of failure. We talk about known or identified risks, the ones that are due to failure modes that we have predicted or that we have found in testing. But then we have the residual risk, the ongoing risk of things we don't know or variables we can't control. To get rid of known risk, these are the things John talked about. Let's do failure mode analysis. Let's do accelerated life testing, reliability growth testing, and we can use HALT here to identify more failure modes, pull them into the known category, and eliminate them. And then, with those extreme stresses, demonstrate that those risks have been eliminated. In satellites, they found HALT to be extremely valuable. We had a nice paper published on using HALT at Space Systems L'Oreal, basically saying we're convinced that HALT was instrumental in the successful qualification program and smooth transition into production. Again, indicating HALT is done before you go into your qual. It's not something you do at the end. You want to do this early and often, and then move into your final qual with confidence. They are also very pleased with the fact that nothing that they have launched has failed due to something that had HALT done on it. If we did HALT, we did very well. So the conclusion is the risk of failure in those environments has been reduced to an absolute minimum. We've pushed it as far as we can. Only problem is failures still happen. Failure modes that are exposed in HALT, they decrease the risk by identifying more sources of risk and getting rid of them. And the graphical way to look at it, if you think of the risk of failure here, where one is I'm absolutely going to fail. We have part of that being identified and part of that being a residual risk. If we don't do HALT, we haven't identified as many risks as we could that are in the design, so there's still a risk of product failure at product release. It decreases over time as we identify and correct things, but then vendor processes or upsets can cause problems later. If you get a halt done early in the design phase, you will identify those failure modes, get rid of those failure modes, and reduce the risk dramatically. You will still have a residual risk of failure, however, because of vendor process changes, that sort of thing. But you've gotten rid of this early life risk. So what do you do to get rid of that residual risk? The unknowns that you don't control, that's where you introduce HASS. And with HASS in place, residual risk can be brought to a minimum. And here too is where the feedback mechanism of failure modes found in the field is extremely valuable for pulling that residual risk line down even further. Every failure, whatever its source, whether HALT, HASS, or in the field, is gold, and it needs to be understood so that you can use those results to reduce your risk. So in summary, it's harder than ever to get reliable products out the door, and it's more critical than ever to get high reliability products out the door. HALT and HASS can be tools that let you do that much more quickly and deliver a product with low risks of failure.
I do have a few questions here, and I will read them to you, and you and or John can respond accordingly. So the first question is, do I have to use accelerated testing to meet third edition requirements?
John, I'll give that to you.
Yeah, let me address that. And the answer is no, you don't have to use accelerated testing to meet the third edition requirements. The requirements are for test, however, and I would suggest that using accelerated test is both time and cost effective.
Yeah, that makes sense.
And so I had a follow-up question to that. Can I use accelerated test techniques to show compliance with all testing required by third edition?
You can use HALT techniques to show compliance with that. Most, in my opinion and in my experience, most of the auditors and regulators, those who approve the design, will accept a well-documented accelerated test.
Okay. And another I have here are any suggestions on helping management understand the benefits of accelerated testing for third edition compliance?
Yeah, that, and I'm sure Neil will have something to add here as well. That is the crux of many issues that we deal with. How do we help management understand the effectiveness and the cost and time benefit of using some of these techniques? And it's never an easy question to answer. I will say, however, that the successes that I have had in doing that come with simplifying the process, understanding exactly what we're going to do, understanding and being able to articulate what the benefits are of using the test compared to other means of meeting the standard.
Yeah, I think one of the problems that you run into when you take the first overall glance at HALT is that it can look complex, and it isn't that complex. And to break it down into a straightforward discovery process helps for upper level management. But one of the most important things that you can do is talk to someone in management who understands what the true cost is of a design flaw that gets into the field and causes a recall. That cost is so extreme that catching one piece of, catching one gold nugget in HALT just makes so much sense to get rid of it early and eliminate the risk of something like that getting into the field, that when you look at the big picture of what that costs and what the impact is to the company and to the public, then anything you can do to reduce that risk further that can be done in a relatively short amount of time, like the HALT&HASS can be done, then it turns into a no-brainer pretty quickly when you look at the big picture like that.
Yeah, I would add that 60601 3rd edition requires test. And you look through the standard, you look through the checklist, and there are many items that are only, the only way to show compliance is through test. So the question doesn't become, do I need to test or do I not need to test? The question in my mind becomes, is there a way to shortcut the testing process by using HALT testing or by using other accelerated test techniques? So not only does it have some time and cost benefit there, but as Neil talked about, it has benefit in identifying the unknown failures. It goes a little bit beyond showing just strict compliance. It shows us, it gives us information that helps us in our design process and helps us make a robust design. So in my opinion, HALT and other accelerated test techniques can get us where we need to go a little bit faster and perhaps a little more thoroughly than just the basic tests that are required. But yeah, it's not a question of whether or not we need to test. It's a question of how we test and how we most effectively and efficiently test.